This is the third section of chapter 9 on constant acceleration, and here we're going to introduce two constant acceleration formulae, and these formulae we can derive from a velocity time graph. So we'll start by drawing a velocity time graph like this. So time here and velocity along this axis here. I'm just going to draw a part of a velocity time graph. So I'm just going to draw something like this. Okay. Now the fact that it says constant acceleration here means that I've drawn a straight line. Yeah. If I had something that wasn't constant acceleration, I would have something like this. Yeah. When you get curves going on, it means that the acceleration isn't constant, it's variable. So I'll just take that out. So we're only interested in constant acceleration. So that line represents a constant acceleration. And what I'm going to do, I'm going to call this velocity here u, and I'm going to call this velocity here v. Now in mechanics, in maths, and also in physics as well, these are standard letters that we use. So here we've used the letter u to stand for the velocity at the start, what we call the initial velocity. So we normally use the letter u when we're talking about the velocity at the start. Velocity at the start. And the letter v we use to represent the final velocity. So on my little diagram here, the final velocity where the line ends, we've used the letter v, and that's sort of standard for mechanics. So this is basically the velocity at the end. Velocity at the end. Okay, so that shows that. Now that line ends here. Okay, and we're going to call that t. T for time. Makes sense, doesn't it? So t for time. We're going to be working out the acceleration in a moment, which is going to be the gradient of this line. So we use the letter A for acceleration. And for displacement, we don't use the letter D, because D sort of could be also mean distance. We use S. So when we talk about displacement, we don't use D, we use S. Now these letters, if I rearrange them, look a bit like a word. SUVAT, SUVAT. So you'll quite often hear people talking about the SUVAT equations, and they're the equations that involve displacement, initial velocity, final velocity, acceleration, and time. So let's see what equations I can get from this graph. Well, the first thing is that the gradient of this line is equal to the acceleration. Okay, so let's just write that down. Gradient of line equals acceleration. Now what is the gradient of that line? Well, it's the change in y over the change in x. Now what's the change in y here? How far up does it go? Well, we don't have numbers, but if I did have numbers, I'd do this number minus this number. Because I've got letters, it's v minus u. Okay, so I'll just put acceleration equals change in, well, it's basically change in velocity, isn't it? That's the change in y over the change in time. Change in time. The change in velocity is v minus u, and the change in time is t. That's the letter we use for the end time. So what equation do I get? I'll get A, acceleration, equals v minus u over t. And then from there, what I'll do, I'll times both sides by t. So I'll get AT equals v minus u, and if I add u to both sides, I'll get v equals u plus at. And this is the first of what we call our SUVAT equations. And this is a SUVAT equation that has u, v, a and t. So if I have any question where I have u, v, a and t, I will use this formula here. Okay, right, what else do we know about that graph? Well, from before we said that the area under that graph, this area here, is going to be equal to the displacement. Okay, area equals displacement. Now if I think about this as a trapezium on its side, sorry I didn't write displacement very well, then I could think of these two sides as the parallel sides. So I've got a side here, and the length of that side there is u. I've got the length of this side here is v, so that my two parallel sides. Then the height of this trapezium would be t. So now I should be able to get another formula. The displacement is equal to the area of that trapezium on its side, and the area of that trapezium is going to be the two parallel sides added together divided by 2 and times by the height, which is t. Okay, so S for displacement is u plus v over 2 times by t, and this is our second, what we call SUVAT equation, because it involves S, U, V and T, so a different combination of letters. So both of these equations have come from this graph, and we can use these equations to solve problems. Now these are all in the formula book, but if you use them lots and lots, you'll just remember them, and it's actually quicker if you remember them rather than having to flick back to the formula book. So the problems we're going to do will involve using one of these two equations, and I'll show you a method we can use to help us decide which one of the two we need to use. Okay, so we've got this cyclist, they're traveling along a straight road. She accelerates at a constant rate from a velocity of 4 meters per second to a velocity of 7.5 meters per second in 40 seconds. In part A, we need to find the distance she travels in those 40 seconds. Now the way that we tackle these questions, or I do them, I write out the letters SUVAT and I see which of these I know. So from a velocity of 4, so she started, our initial velocity is 4, to a velocity of 7.5, so she finished at, in this part of the journey, a velocity of 7.5, and that took 40 seconds, so the time is 40 seconds, and we want to work out the distance she travels in those 40 seconds. Now in this case, that the distance she travelled will be the displacement, because she's not moving backwards, she's just moving forwards. Okay, so this is what we need to find. So S is what I need to find, and I know U, V and T. So I want one of those equations, those SUVAT equations, that has S, U, V and T in it, and that equation is going to be S equals U plus V over 2 times by T, and it's often useful to write these equations out. Yeah, if you write it out before you use it, it just gets you used to remembering them. So we're trying to find S, U is 4, V is 7.5, so we just substitute these values in, and we times by T, which is 40. Okay, so that will give me S equals, we'll do this on my calculator, 4 plus 7.5 divide that by 2 times by 40, and I get a value of exactly 230. So 230, and this is in meters. So it's as easy as that. Writing out SUVAT, deciding what you know and what you don't know, what you need to find and what you don't need to find, and then choosing the correct equation. Okay, part B, acceleration in these 40 seconds. So I'll write SUVAT out again. So U stays the same, V stays the same, T stays the same, but this time I'm trying to find A. Now notice in the first one A was left blank because I didn't need to find it, and this one S is left blank. Now I could put the 230 here and use it for S, but if for some reason I get this part wrong and I use an incorrect value here, then it's going to affect my next answer. So if possible, avoid using previous answers in case they're wrong. Sometimes you have no choice, you have to use it, but in this case I don't need to. As long as you have 3 unknowns and you're trying to find a fourth, we can use a SUVAT equation. So this time I'm looking for a SUVAT equation that has U, V, A and T in it, and that one is V equals U plus AT. So just like before, we substitute in. So V is 7.5, U is 4, plus A that we're trying to find times by 40. So we'll start by taking 4 away from both sides, and that will leave me with 3.5. So I've got 3.5 equals 40A. So A is going to be equal to 3.5 divided by 40. So let's work that out. 3.5 divided by 40 will give me a value of 8/70, which I suppose I could write down. That's going to be exact, or 0.0875. So exact is a fraction, so I could write 7/80 meters per second squared, or press the SD button and get 0.0875 meters per second squared. Now, since you're allowed to give answers to 3 significant figures, if you wrote 0. Well, that would be 3 significant figures, so that one wouldn't change. Yeah, so remember, minimum 3 significant figures, so don't round this to 0.09. yeah, you'll lose a mark for doing that. So 3 significant figures minimum. Okay, or in some cases that might be the maximum you're allowed. Yeah, but if you always stick to 3 significant figures, you won't go wrong, unless the question says give the exact answer. Okay, so I'll just start by drawing this as a diagram. So we've got this particle at point A, and it's decelerating, and then it gets to point B. At point A, the velocity is 8. At point B, the velocity is 2, so you can see it's slowing down. And it said it's decelerating at 1.5. So we use the arrow like this to show acceleration. And I'll put negative 1.5 meters per second squared. And what we need to do in part A is to find the time taken to get from A to B. So we write out SUVAT like this and fill in what we know. Well, the initial velocity is 8. The final velocity at B is 2. The acceleration is negative 1.5 because it's a deceleration, and I want to find the time taken, so I want to find t. So that means I'm going to be using the equation V equals U plus AT. So So we just substitute in the numbers. 2 equals 8 plus negative 1.5 times by t. So we'll take 8 away from both sides, which will give us negative 6 equals negative 1.5 t. So this will give us t equal to 4, so that's 4 seconds. So that's the time taken to move from part A to part B. So I might actually add that to my diagram because that might be useful in a minute. So I will just put 4s here, so that's the time to get from A to B. Part B, we want to work out the distance from A to B, so we want to work out S this time. So I'll put a question mark here. U is still 8, V is still 2, A is still negative 1.5. Now I could, if I wanted to, use my answer for T from part A, but I don't need to. I only need 3 knowns to find a 4th unknown. And I would say avoid using previous answers if you can, in case it's wrong. Because if I get this wrong and I use T here, I'm going to get an incorrect answer and I'm going to lose at least 1 mark. So if possible, try and avoid using it. That's not always possible. You know, sometimes you have to use your previous answer. So S, U, V and A, that's going to be, well actually I think we do need to use T, don't we? Because the formula is S equals U plus V over 2 T. So yeah, I'm going to have to use the answer. Now later on you're going to see that we have other options. There are other SUVAT formulae that we can use where we wouldn't have to use this. So unfortunately we're going to have to use it. So let's hope that part A is right. So S is going to be U plus V. So 8 plus 2 over 2 times by T, which is 4. So that'll give me S as 5 times 4, which is 20. So the distance from A to B is 20 meters. So let's put that in on my diagram as well. So my distance here, 20 meters. I've got quite a lot of information there. Right, that might be useful for the next bit. So before we get to part C, it says after reaching B, the particle continues in a straight line with constant deceleration 1.5 meters per second. The particle is at point C 6 seconds after passing through point A. Find, right, let's add this. So it continues to C. Now what it's saying is that it takes 6 seconds from A to get to C. So actually this portion of the journey here is 2 seconds. And we want to find the velocity here. So what we're going to do is, just like before, we're going to write out SUVAT and see what we have and see what we want to know. Now there's a couple of ways we can do this. We can take this as the initial velocity, 8, and take this as the time, 6, to find the velocity here, because the acceleration is the same throughout the whole journey. Or we can take 2 as the initial velocity and take the time as 2 for just this part of the journey and work out the final velocity here. I'm going to take 8 as the initial velocity and take the time as 6. So I'll just put in brackets the alternative. So the alternative is that you take U as 2, that's basically at B, and you take the time as 2. So that's just looking at the journey from B to C. That will also work because the acceleration is the same. So, or deceleration. So negative 1.5, because that stays the same in that part of the journey, and we're trying to find V. And actually I might work it out both ways and show you, one in blue and one in black. So taking the initial velocity at A, so V equals U plus AT, So v equals 8 plus negative 1.5 times by 6. So that will basically give me 8 minus 9. That will give me v equals negative 1. That basically means it's now moving the opposite direction. If I do the alternative way and use the initial velocity u as 2 and the time as 2, I also get the same answer. I'll still get v equals negative 1. Okay, so I could do it either way. So the velocity is negative 1, which means it's now slowed down so much it's come to a stop and then changing direction. A bit like if you were to throw something in the air, it reaches a point at the top, changes direction and then falls down. And then the last bit here, part D, the distance from A to C. So SUVAT again, trying to find S this time. So I'm going to use U as the 8, the T as the 6, and the A as the negative 1.5. Oops, negative 1.5. Now, since I don't yet have a formula that has SU, A and T in it, I need V. So V is going to be the velocity at C. So notice here I want to find a distance from A to C. So I've got the velocity at A and the velocity at C. So I need these two velocities if I'm going to find this distance. It's no good having this here. Okay, where I could actually find this distance between B and C and add it to 20. Okay, that's an option, but I'm going to find the distance from A to C, so I need a velocity at A, a velocity at C, which I've got the deceleration, I've got the time. I want to find S, so it's going to be S equals U plus V over 2 times by T. So S will equal U plus V, so that's going to be 8 plus negative 1 over 2 times by 6. So if we just work that out, basically becomes 7 over 2 times by 6, and we're going to get a value of S as 21, and it'll be 21 meters. As I said, the alternative, and you could try this yourself, to find the distance from A to C would be to find the distance from B to C and add it to 20. And to find the distance from B to C, you would use a time of 2, an initial velocity of 2, a final velocity here of negative 1, that's the one that we worked out, and using those values of U, V, so basically 2 plus negative 1 divided by 2 times by T, which would be 2, you will get the same answer. Well, you wouldn't get the same answer, you would get an answer of 1 meter, which you'd add to 21. Actually, let's work that out and see. So let's work out what this distance is here. So working out S equals U plus V over 2 times by T. So S is, or U is 2 plus negative 1 over 2 times by T, which is 2. So what do we get for S? So that's 1 divided by 2, half times by 2, but that's just 1. Okay, so that's the displacement in this part. If you then add that to 20, you get the same answer. Okay, so here we got a car moves from traffic lights along a straight road with constant acceleration. All the problems to do with SUVAT are to do with constant acceleration. The car starts from rest. Okay, that means that the initial velocity is 0. Something starts from rest. at traffic lights, and 30 seconds later, okay, so there's a time, it passes a speed trap, which is like a speed camera, where it is registered at travelling at 45 kilometers per hour. Find, in part A, the acceleration of the car. Okay, now the first thing we do before we use SUVAT is we need to convert this kilometers per hour into meters per second. So 45 kilometers per hour is the same as 45,000 meters per hour. That I just times that by 1,000. So I want to work out how many meters that is per second. So I need to divide by 3,600. That's how many seconds that are in an hour. 60 times 60. So actually not times by 3,600. Divide by 3,600, and that'll give me 12.5 meters per second. So now I'm ready to use SUVAT. So SUVAT starts from rest. U is 0. It's traveling at 45 kilometers per hour. 30 seconds later. So time is 30. V is 12.5 meters per second. That's the 45 kilometers per hour. So they're my 3 knowns, and my 1 unknown is the acceleration. So the equation that's going to have those in is going to be V equals U plus AT. So we just substitute in 12.5 equals 0 plus A times by T, which is 30A. So A is going to equal 12.5 divided by 30. So let's work that out. We'll get an acceleration of 5/12 meters per second squared, or if we press the SD button, we're going to get 3 significant figures. 4, 1, rounds to 7 meters per second squared. Okay, so that's 3 significant figures. Part B says the distance between the traffic lights and the speed trap or the speed camera. SUVAT again. So these values we know: U, V, and T. And we're trying to find S. So we're going to use S equals U plus V over 2 times by T. So we don't need to use our acceleration from part A. So that will give us S equals 0 plus 12.5 over 2 times by 30. So what do we get from S? That's basically 12.5 divided by 2 times by 30, and we get 375 over 2. That's S, it's meters, and we'll probably want to write as a decimal, so that's 187.5 meters. Let's just know what those answers. Yeah. Okay, should now be able to do exercise 9C on page 140. So a quick recap. We've been introduced to these constant acceleration formulae. So where the acceleration doesn't change. We got them both from a velocity time graph. One is V equals U plus AT. The other was S equals U plus V over 2 times by T. And we have this thing SUVAT. So remember, S is displacement. U is initial velocity, the velocity at the start. V is the final velocity. A is the acceleration, and t is time. So if we were to look at this first formula here, SUVAT, so we would use this when we have U, V, A and T, and if we look at this one down here, and again SUVAT, we'll use this when we have or want to find S, U, V and T.